Hi everyone, today our Group K is going to present a journal which the title of the journal is Comparison of COP in a Refrigeration Cycle for the Most Promising Refrigerants in the Future. This is the overview of our presentation, which include introduction, schematic drawings, performance calculation, performance analysis, conclusion, and suggestion of system improvement. Firstly, this journal investigates the impact of different configuration and working fluids in refrigeration cycles. It analyzes and compares refrigerants R134A, R600A, R152A, R507A, and R1234ZE as working fluid for refrigeration cycle. Each of the refrigerant is compared between simple and cascade refrigeration cycle in different thermal flow. This study was carried out to understand how different refrigerants behave in varying climate conditions, which are in Bogota, Medellin, and Barranquilla, Colombia. This study has applied EES software to evaluate variables such as coefficient of performance, COP, compressor work, SSG structure. The objective of this study was to identify a refrigerant that have an inherent balance between operational efficiency and environmental sustainability emerges. Table 1 shows the environmental condition of three thermal flow chosen, which are Barranquilla, Medellin, and Bogota for the refrigeration cycle designs. By referring Table 1, we can know the main condition of the thermal flow, which are temperature, pressure, and altitude. Besides, we can use Table 1 to determine the properties of the first state of the simple and cascade refrigeration cycle. Other than that, Table 1 can also be used to identify the mass and energy balances necessary to evaluate the process.
There are two schematic drawings in this journal, which are simple refrigeration cycle and cascade refrigeration cycle. Figure 1 shows the schematic drawing of a simple refrigeration cycle. A refrigeration cycle is just like any other cycle which has a flowing medium that is known as refrigerant that flow throughout the cycle. There are four main components in a refrigeration cycle, which are compressor, condenser, expansion valve, and evaporator. The condenser and the evaporator work as heat exchanger, which heat is rejected in the condenser and heat is absorbed in the evaporator. At the compressor, the vapor refrigerant will be compressed to increase its pressure and temperature, and the refrigerant after the compression process is now in vapor state. The refrigerant exits from the compressor then goes into the condenser. The temperature of the vapor refrigerant decreases, but the pressure remains the same. The vapor refrigerant will change its phase into liquid and become liquid refrigerant. After that, the liquid refrigerant will then enter the expansion valve as a liquid and exit the expansion valve as a saturated mixture. This is because the expansion valve will lower the pressure and temperature of the refrigerant. The saturated mixture refrigerant will now enter the last component of the refrigeration cycle, which is the evaporator. The evaporator will evaporate or vaporize the refrigerant. The refrigerant that exits the evaporator is in vapor state and it flows back into the compressor to start the process again. This is how a simple refrigeration cycle works. Figure 2 shows the schematic drawing of a cascade refrigeration cycle. A cascade refrigeration cycle will have two or more refrigeration cycles in series. A cascade refrigeration cycle is normally used for industrial purpose because industrial application normally involve a large pressure range and large temperature range. If a simple refrigeration cycle is used for large temperature and pressure range, it will result in poor performance of reciprocating compressor, which decreases the efficiency of the refrigeration system. In this journal, they also provided the entropy diagram for the simple refrigeration cycle and the cascade refrigeration cycle.
For the performance calculation part, we have shown a few important formula that were used to carry out this research. Table 3 shows the general design parameters which are chosen that will be kept constant in order to be able to infer the behavior of the fluids in the different technologies. Table 4 shows the fundamental equation for the thermodynamic analysis of the simple refrigeration cycle. Based on the Table 4 and the entropy diagram of the slide before, we can know that from state 1 to state 2, it is an isentropic compression which entropy is kept constant during this process. Besides, enthalpy H is kept constant from state 3 to state 4. From state 2 to state 3, it is a constant pressure heat rejection process, while from state 4 to state 1, it is a constant pressure heat absorption process. Next, to calculate the coefficient of performance of simple cycle, the formula used is QL divided by W net in, which is also equal to H1 minus H4 divided by H2 minus H1, where H is equal to enthalpy. Other than that, the exergy destroyed equation also was used to calculate for each process, where exergy destroyed is equal to T naught times S2 minus S1 plus QK divided by TK. For the analysis of the cascade refrigeration cycle, mass flow rate can be calculated using the equation m dot A times H5 minus H8 equal m dot B times H2 minus H3. Last but not least, we can also determine the COPR for cascade refrigeration cycle using the formula COPR cascade equal Q dot in divided by W net in, which is also equal to m dot P times H2 minus H3 divided by m dot A times H5 minus H8. All the calculation was done by using engineering equation solver software, which is also known as EES software.
Next, for the performance analysis, this table is the result obtained after the parametric study of the refrigerant. For the first point is about COP refrigerant in simple cycle with COP refrigerant in cascade cycle. We get to know a lot of information by interpreting and analyzing table 5 and the graph in the journal. So based on the COP refrigerant graph, it shows a trend to be higher in the cascade refrigeration cycle compared to a simple cycle, which is due to its configuration and characteristic. This is because cascade cycle use multiple stages of compression and condensation. This reduces energy losses and increases overall system efficiency. On the other hand, simple refrigeration cycle operate with a single compression stage, which increase pressure from evaporation to condensation in a single step. This results in consuming more energy. For the next point is the comparison of the compressor work in simple cycle with compressor work in cascade cycle. In colder climates, the heat load that the refrigeration system must manage is usually lower. This results in higher COP refrigerant and lower compressor power consumption, since the system does not have to work as hard to extract heat from the area that needs to be cooled. Besides, simple refrigeration cycle has a higher compression work compared to cascade refrigeration cycle. For the last point is about exergy destroyed in simple cycle with exergy destroyed in cascade cycle. As the ambient temperature rises, more energy is destroyed in all refrigerants. However, there is no significant change in energy destruction with a change in thermal flow. The variable that does affect the exergy destruction is the technology applied to the refrigeration cycle.
Conclusion. This journal highlights two main findings regarding refrigerants and refrigerant cycles. The first finding is refrigerant R1234ZE stands out among the other refrigerants due to several reasons. First one, it has a high coefficient of performance for refrigeration, COPR, making it highly efficient. It requires low compressor work which reduces energy consumption. It results in minimal energy destruction, enhancing overall system efficiency. This study also shows that the cascade refrigeration cycle performs better than the simple refrigeration cycle. This advanced cycle configuration achieves superior efficiency and effectiveness, particularly in applications requiring lower temperatures. In summary, selecting refrigerant R1234ZE and implementing cascade refrigeration cycles can significantly improve the performance and efficiency of refrigeration system. Last but not least, suggestion on system improvement. 3 suggestions have been given for system improvement, which are multi-stage and cascade cycles, refrigerant optimization, and eco-friendly practices. Firstly, we can implement multi-stage and cascade cycle to significantly enhance efficiency, especially for low temperature applications. These advanced configurations achieve lower temperatures more effectively, though they come with increased complexity and cost. Besides, it is crucial to choose the right refrigerants. We should prioritize refrigerants with low global warming potential GWP and zero ozone depletion potential ODP. This may involve redesigning system components to maximize performance with these eco-friendly refrigerants. Furthermore, adopting eco-friendly practices such as improving energy efficiency and using sustainable methods are essential. This includes optimizing component designs and utilizing renewable energy sources to reduce the environmental impact of refrigeration systems. In summary, by implementing multi-stage and cascade cycle, optimizing refrigerant choices, and adopting eco-friendly practices, we can significantly improve the performance, efficiency, and sustainability of refrigeration system, at the same time reduce environmental footprint.